4.4, we're going to be taking a look at the dot product. We started it last time. Let me remind you a couple of details and before we go over to the properties that we were working with. To start with, the dot product actually takes components and multiplies them, right? So the I components coefficients get multiplied, the J components coefficients get multiplied, and then we add those results together. And when that happens, we end up getting a number or a scalar at the end, okay? And we had been doing a few examples. We had gotten to the point where we saw an example where the commutative property happened. And sure enough, it didn't matter whether we did u dot v or v dot u, we get the same thing. We saw a distributive example where we could take the dot product of something that was added and we could do the dot product individually with those vectors and then add them. And now we're actually on to the last two properties that I want to mention for you, okay? All right, so magnitude is the next one. Now we talked about magnitude in section 4.2, or 4.3, excuse me. Magnitude had this equation, so let me just write it down so that it seems quite reasonable when we look at this property for magnitude. The magnitude is the square root of the I components, which we'll call them A, and the J component, which we have traditionally now called B squared. Okay, so nod your head if that looks familiar. We talked about the fact that this is really just the Pythagorean theorem, or it's a version of the distance formula as well. All those things are interplaying together. And if I were to square both sides, what you can actually see that we will have is then just a squared plus b squared on the right, correct? Sure, the square and the square root here would cancel. Mark those so you can see them. This square root and this square would cancel. We would have the a squared plus the b squared. This would say the magnitude of v squared on the left. And if you take a look at what it is that we do when we do dot products, that's exactly what we do. We take the I component and we multiply it by itself. Well, if the vector is itself, then that would just be the same A multiplied by itself. And the same thing for the J component, the B multiplied by itself. So the magnitude has this property. The last one, zero vector, is a pretty straightforward one as well. When you multiply the zero vector by anything, you get a scalar of zero. And the reason that that makes sense is because the zero vector just has all components of zero. So if I multiply 0 over here in this property, right, if one of my vectors is actually, let's put it in right here, 0, 0, and I multiply each of those zeros by other components, I end up getting a 0 overall. Make sense? Okay, so those are our basic properties for dot products. And the next thing we're going to do is we're going to actually look at an alternative definition of the dot product that does involve the angle, right? Everything else has involved only the components that we had looked at. And now we're going to take a look at a connection to the angle measure that is between our vectors. So we're going to let v and w be vectors, and theta is the angle between them. So remember what that would look like, and I'll just draw you an arbitrary kind of picture. If we have this vector and we have this vector, right? It doesn't matter where they are in space. You can actually pick one of them and up, and you can put them end to end. Or you can put them end to end like this, depending on what you're sort of looking at, right? This is the one that we would like to take a look at for the argument here, for what we're describing here. So if we put them end to end this way, this is the angle theta that we're referencing, okay? So the A and the B's, right, those vector components that we were looking at before, still get multiplied in the same way. On the left-hand side, and on the right-hand side, this is saying that we could actually take the magnitude of v and then the magnitude of w, right? Those are square root values, and then we can multiply by the cosine of this angle measure. So we can actually use the dot product to find the angle measure between two vectors. This is the first time we've had the ability to find something like that. All right, so here's an example. We are being given vectors v and w, and we're told that we want to find the angle between them. So the formula from the previous slide, I'll rewrite it over here, is that the dot product of v and w is equal to the magnitude of v times the magnitude of w times the cosine of theta. That's our formula. So dot product on the left. We've done some of these, but it's been a weekend, so let's make sure we're careful to do them together. To do the dot product means we multiply the I components. This is negative 3 times 5 plus, and then we multiply the J components. This is 4 times 12. And that will be the dot product, and that's the left-hand side of this equation. Okay. That should feel very familiar. We've done several of those, even if it has been a weekend. Okay, is that part okay? Okay. Magnitude then means taking the square root, and we take each of these components and we square them. So feel free to use the negative if you wish. It is -3 quantity squared, but that's the same as 3 squared. Plus, and then we do the 4 squared. And then I'm going to do the W. I have a 5 next. That's kind of funny. They're in order. 3, 4, 5. I have 5 squared. And then I have a 12 squared. And then it is the cosine of theta. So because I'm being given the vectors to start with, I have all the components, or all the pieces rather, that I need in order to find the dot product on the left and to find the magnitudes on the right. The only thing I don't know is the angle, which is in fact what I'm asked to find. So we're going to take a look at what each of these are. We'll do the left-hand side. So this is -15 plus 48. And then on the right-hand side, when I take the square root of 3, the square root of 3 squared plus 4 squared, do you know what this quantity gives me? It's a square root of 25, which will be 5. It's a very friendly one. They don't always end up coming out of square roots. This one did. The second one actually will as well. If you take 5 squared plus 12 squared, and then you square root it, what are you going to get?
13.
Yeah, so we have the square root of 169, so this piece is 13. So 5, and I have 13, and I have the cosine of theta. We'll add the pieces together on the left, we'll multiply the pieces together on the right. So -15 and +48 is what? 33. Mm-hmm. And then if I have 5 times 13, what do I have?
65.
65. Okay, now this point, what do we do? We will divide by 65. And you're welcome, if you wish, at this point, right? So I can mark out the 65s, to go ahead and do the inverse cosine, right? That's what we're going to have to do. We're going to have to do the inverse cosine of both sides. It doesn't even matter if 33 over 65 could simplify. It's sort of irrelevant to the discussion. Make sure you're in degree mode. So check that if you haven't been working with a particular calculator we're with for a little bit. And it tells us at our directions that we're going to round this one to the nearest tenth of a degree. What does that mean? Just 1 decimal. So looking at the value that your calculator spit back out at you, if I round that to the nearest tenth of a degree, what will you get? 59.5 degrees. Okay, is that all right? We're all good, yeah? All right, let's take a look then at a couple more. We keep coming back to this, where we do a little bit of a definition or a little bit of a theorem, and then we look at some examples, especially because this is new kind of a topic for us. So we're going to do that again a little bit here. We're going to talk about what it means for vectors to be parallel. It's similar to what it means for lines to be parallel, but it is a little bit different too. So we want to be a little bit careful here. So 2 vectors are parallel if the angle between them is 0 degrees or 180 degrees. Now that is not at all how we sort of describe parallel lines, but the image is quite the same. So I'm going to draw a vector, and if I can draw it well, so I'm going to copy paste so that I make sure that it is. We would say that those 2 vectors would be parallel if we just looked at them from a line perspective, correct? The lines themselves that make up that piece of them, they look to be parallel. That's why I copied and pasted, so I made sure that it really worked, right? But the reality is that I can also take this and I can make it longer. So you don't have that, and it makes it look thicker just because of the way I'm enlarging it. But you don't have that sort of property inside of lines because lines are infinite creatures, right? They go in both directions forever. Vectors actually have a size. They start somewhere and they end somewhere. So vectors can be parallel even if they're not the same length or the same size. In order to mean that they are 0 degrees and 180 degrees, let me draw those pictures, and these 2 are 0 degrees. So 0 degrees means that they are going in the same direction, right? And remember, we can move vectors wherever we want. So it doesn't matter where they're located in terms of space. These would have 0 degrees between them. And if you think about it from the perspective of what I did before, again, if you put them end to end, or if you tried to put them like I did over here, end to end, there would be no angle created, right? All right. The 180 degrees actually means that what I can do is I can take this and I can actually go the other direction. So let me change colors just so it's drawn differently. If the vector looked like this, again, size doesn't matter, but it's going in completely the opposite direction. This one's easier maybe in some ways to see that there's 180 degrees from here to here, right? And again, it doesn't have to be drawn here, right? It can be drawn anywhere in space, but you can see the angle measure still by putting them end to end because we can move vectors at will and it doesn't change them. Okay, vectors are regardless of space. There's no regard to space where they are in the coordinate plane. We can actually describe vectors being parallel with an equation as well. So vectors v and w are parallel if and only if there's a scalar k such that kv is equal to w. Okay. Notice there's no restrictions on k. K can be positive, k can be negative, it can be a fraction, a decimal, it can be a whole number, it can be big, it can be small, it doesn't matter what it is. It can be rational or irrational, anything you'd like for k. As long as you multiply one by the other, you're going to get parallel vectors. So determining if vectors are parallel, you can look at the angle between them, but that's not really the easiest way to do it. It's far easier to look if one is a scalar multiple of the other one. So as we take a look at our next question, that's going to be our approach. It says we're going to determine whether the vectors are parallel. And we have a vector that's v, which is 3i plus 5j, and we have a vector w, which is 6i plus 10j. And what we would be looking for, and you can put the v or the w on either side, it doesn't matter, is if there is a value k that you can multiply 3i and 5j both by to get 6i and 10j. Now I think this is probably the most natural setup, because I think it's easier to see what I would need to multiply 3 by to get 6 because it gets bigger than to go the other direction, right? Now it's true the other direction, I'll show it to you, but what number would I need to multiply 3 and 5 by to get 6 and 10? 2, right? This one's pretty simple to eyeball it, right? If it weren't, right, let me just show you what you would do, because sometimes the numbers, if they give you decimal numbers or something like that, or fractions, you might not be able to easily see whether this works. Agreed? But this one's very friendly. That's the whole point of it. But you would actually be able to multiply this through, and you could say, okay, well, 3k needs to equal 6, and 5k, right, needs to equal 10. And you just solve both of them. And if they both solve to giving you the same k value, which these do, right, here k equal 2, here k equal to 2, then yes, this is going to work. If when you solved these, they gave you different k values, then it wouldn't work. Does that make sense? So this ones are parallel. So V is parallel to W, and that's our notation for parallel if you haven't seen that in a little bit for a geometry kind of perspective. If you had set it up the other direction, it still works. We could still say that we would multiply, we would need to get 3i plus 5j when we multiplied k by 6i plus 10j, right? The only difference when you multiply this through and do all the things is that k ends up being a fraction. But because we said that k can be anything we'd like, there's nothing wrong with it being a fraction. It's just a little bit less obvious to see the number show up when we go from a bigger value to a smaller value. Is that all right? Okay. Our next one we're going to look at is kind of the comparison that you would make from a geometry standpoint. The two things that you look at in geometry are parallel and perpendicular. Nod your head. That should sound very familiar, right? Okay, so when we're working with vectors, Orthogonal is the word that's used to describe things that are perpendicular. So jot down next to yourself that this is just another word, but it's done and it's used in vector form for perpendicular. And as you see it described, you see that show up, right? Two vectors are orthogonal if the angle between them is 90 degrees. Well, that's what it means to be perpendicular, right? That the angle that they create, right? When you think about lines, so if we were working with lines here and the lines were perpendicular, it would mean that they create a 90-degree angle, correct? The same thing's true for our vectors. If we're working with our vectors and they are orthogonal, it means that they create a 90-degree angle between them. Okay, so orthogonal means perpendicular based on your previous knowledge. Perpendicular, orthogonal, is actually really easy to decide if something is orthogonal. If they're orthogonal, then their dot product is 0. It's lovely. So it's an easy thing to check for. So easy to check for. You just find the dot product, and if the dot product's 0, it's orthogonal. And if the dot product's not 0, it's not orthogonal, right? It's easier to decide if things are orthogonal than to decide if they're parallel, especially given certain values, right? This is a little bit messier of an equationing process than it is if you were working, if you're working with decimals and so forth, than if you were trying to find the dot product. Okay, so we're going to decide if something is orthogonal. When we decide if something is orthogonal, it's asking us if the dot product is 0. That's the equivalent question. Is it orthogonal? Okay, I just check if the dot product's 0. So let's find the dot product. So what will be the dot product of V and W here? Well, somebody tell me what numbers I'm going to do. What am I going to multiply and so forth? What am I doing? 2 times -9, and then what? -3 and -6, and in between them is a plus. It's addition, yeah. Okay, so what's -2 times -9? -18, and -3 times -6? +18, and sure enough, those add together to be 0. So yes, they are orthogonal. Now, could you verify this by graphing them? You certainly could. It would be less accurate because there's always a little bit of inaccuracy when we graph things, right? Some are more accurate than others. Do you have a grid? Those sort of things. But it should be a reasonable way to decide, quickly, like, does that seem like it makes sense? But the dot product itself is not a complicated process. All right, any questions about dot products? All right.